Waves flashcards. This is for me and probably you lot. So basically I'm going to make flashcards. I'm going to explain all of the stuff. Some of the stuff is very self-explanatory, others will probably need explaining. So these are going to be individual flashcards. There's going to be 15 of them, and they're just going to summarize the key points in each topic. So this is probably going to be really long because it's going to be the entire Waves flashcard stuff, but we'll see. So the first one is the key terms. So these you will need to memorize. So displacement, I'm going to make these as simple as possible. So distance from equilibrium, literally is the distance from the equilibrium. Equilibrium is basically the start point or zero. Amplitude, distance from the middle to the very top. So if we were to draw a wave, which I will, so the wave shall be here. This is the middle of the wave, and we're going to draw a basic longitudinal wave, which will look something like that. So the amplitude is this part, so the distance from the middle to here. So next, wave length. The wavelength is the distance between one wave and the same part on another wave. So for example, let's just say this wave right here, the first part is here, and the wavelength would be the part to the same part on the next wave. So that would be the wavelength of the wave. So next is the frequency. Spelling doesn't matter, but frequency, and that is the number of cycles per second. So a cycle is basically a full 360-degree turn. A full 360-degree turn in this case is one wave. One wave is measured in radians, and one radians is 2 pi, and because of that, that means that the frequency is just one cycle. So now, wave speed. This is the distance per second. So obviously you know the definition for speed is distance per second, because obviously meters per second, and that is predominantly the reason. So now phase difference. This is the amount with which one wave is behind the other in radians. So say you had a wave, and this wave was built up like this, so it went that, Jesus, oh no, that, and then it went down, 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 up, 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 down, down, down. So the phase difference from, say, the point here, that wasn't intentional, to the point here. Oh, I've drawn the wave completely wrong there, haven't I? Oh, for God's sake. So the wave should look something more like that, and then it goes that way. So the difference from the point here to the point here would be pi, theoretically, which is 180 degrees. And because one whole wave would be 2 pi, or 360 degrees, so half of that, which is this part to this part, would be half of 2 pi, which is just pi. Simple. So next is path difference. This is something which is measured in meters and would be the difference between the length of two waves. So say you had two different waves, the path difference would be the difference between the length of those waves. That is very self-explanatory. Go back to black again, and progressive. These are waves whose oscillations travel and transfer energy. Waves whose oscillations travel and transfer energy. So that is mostly every wave, although we do know that like stuff like transverse waves don't actually travel, they only send energy through vibrations. So that is one. This is going to be a long video, you know. Right, let's do this one quickly. This is longitudinal and transverse waves. So very simply, there are differences you need to know. You need to know how they look. So as far as longitudinal waves go, they are all at the speed of light. They travel. They are all EM waves. So every EM wave is a longitudinal wave. They travel perpendicular to the direction the wave should go. This is like, say, the energy travels perpendicular, but the wave should obviously go this way. But in this case, the energy goes up this way and then comes back down and then goes up. So that would be considered in the energy would move at right angles. There you go. And what else? Oh my god, I have F this hard. This isn't longitudinal waves. This is... I'm an idiot. This is... Hello? Testing, 1, 2, 3, 4. This is transverse waves. Oh, I'm an idiot. Transverse waves. Yeah, so transverse waves, energy moves at right angles, travels at speeds of light. They do not need a medium to travel through, so they can travel through space, obviously. So those are like the main points that you really need to know about transverse waves, even though I probably F that. Now, longitudinal waves, these are a bit different. These are the waves that don't look like a wave. They are a series of refractions and compressions. The energy would move in the intended direction, and that would be parallel. So in longitudinal waves, the energy would actually move, hello, this way. Well, that's meant to be straight, and there will be a series of refractions and then compressions, so stuff like that. So kind of imagine a slinky in a way. So they do need a medium to be able to travel. Simple. So that is mostly all you need to know for longitudinal and transverse waves. One needs a medium, one doesn't need a medium. One of them travels at the speed of light and are EM waves. Others are stuff such as sound waves. Okay, then now superposition and interface. Superposition and interface. Simple. So let's make that bigger. So basically, the point at which waves meet is called superposition, where the waves meet, and the total displacement at a point is equal to the sum of the individual displacements up to that point. So sum of displacement equals individual displacements up to the point. Well, that should be very self-explanatory. So there are two types of interference. constructive and destructive. So constructive let's just call it that, interference, when they are in phase with each other. So phase is like kind of like they are the same direction moving waves in a way. They are the same, like they are the same radians, so they both look like, give us a second, they both look like that and that, so they're both in the same phase apart from looking like that and then that, which leads me on to destructive interference, and that is when they are not in phase, e.g. when they are 180 degrees out of phase. So that's when they're not like equally in the movement phase. So the best way to explain this is through the use of peaks and troughs. When waves are in phase, two peaks and troughs would constructively interfere, and this would cause a double peak or trough to be created. When waves are in anti-phase, a peak would meet a trough and would cause destructive interference. So obviously what that would mean is, here is our wave 1, which looks like this. That was not intentional. And here is wave 2, which looks like this. Oh, for God's sake, this is meant to be more down here. So that. So these are in phase because the troughs and the peaks are in line with each other. While, let's say, we had this wave here, and then we had this wave here. These are not in phase with each other because obviously the trough would meet the peak, thus causing destructive interference. So that is the next part. So now stationary waves. This is kind of like an okay one. Stationary waves. I quite like that blue, but we are changing back to black. Stationary waves. So this, I cannot be bothered. Am I blind? This is racism at this point. The hell? But you can't choose black. Okay, this is a wave which stores energy instead of transferring. So that is very simple. So the process of making a stationary wave, that is 1. A wave is made, and this wave is reflected and goes the opposite direction from which it came. So I think that probably would be quite confusing, so I'll explain. So the wave is made here and it goes that way, then it is reflected and it goes back that way. Simple. So 2. Let's just make this big again. That really annoys me. Give us a second. 2. At the other end, this reflected wave would go back to the opposite and the frequency of the wave generation at the length of the string would mean that there would be superposition. So we already know that what that means. So 3 at the place where the waves are in phase, they would meet constructive interference and would form a maximum point, which would be called an antinode. And then number 4, finally, at the point where there is anti-phase, there would be destructive interference. So I will explain what this all means. This means that, okay, so I understand now. So basically what it is say you had like a skipping rope. That is probably the best example for this. And on the skipping rope you had one person here and he was holding it, and you had another person here who was holding it. Say the first person was to just like move it up and then down very quickly. The skipping rope would then just do this, and then it would get to his hand, and then it would bounce back again. So the basic premise of stationary waves is that instead of that happening, what would happen is they both move it in a kind of like unison to create a harmonic. Harmonics are basically stuff like, say when you jump rope, the spinning motion off the rope is the first harmonic. The second harmonic is 2 of these, so say this is happening, then that's happening, and then one's spinning this way and one's going up that way. That would be the second harmonic, and that's basically what a stationary wave does. It creates harmonics by making 2 waves act in par with one another. So next. The next is the fundamental frequency of a wave on a string is found by 2 equations, and here are the equations. So fundamental frequency, and now the equations are frequency equals 1 over 2L, which is length, and this is all times by T over U to the 0.5. 0.5 means squared. The next formula is T equals mg, and then U equals ml. And from the equations you can tell by raising the tension, or if you shorten the length, it would mean that there would be given a sense of an increase in pitch, which would be significant in this case. So, double slit interference, that's probably where we'll end it, but double slit interference. Let's get it. So, this is Young's double slit experiment. This is when 2 double slits are lit up. The 2 slits would act as coherent, so like wave sources. Coherent, this means that the waves would have the same frequency with a constant phase difference. We've already been through what phase difference means. The light would diffract at the slits, and this would cause 2 waves to form. And the formula for this would be W equals H, that's the Greek H, D over S, or in words that would be fringe spacing equals wavelength times distance divided by distance from slits. So what this basically is let's say we had a laser, the laser shoots light, the person has made a massive cube, inside said cube he has split it up into parts, like these are tiny slits, and then he fires a laser and or a light at it, and then the waves would diffract inside the stuff, inside the chamber, and that would basically be it. That is the waves topic, or half of the waves topic, because I can't record more than this, but we'll see.